Can everyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey. We are here on site in Jenny Jump State Forest in Hope, New Jersey. So since I see a couple people who are just finishing up parking and wandering down, I'm going to give them a couple minutes to find their way down here, pull up a nice patch of dirt or grass, and get settled in. I want to welcome everyone, not only everyone who's joining us here, but also joining us online, because that's right, we do live stream these to both YouTube and Twitch. So if you're ever at home, bored out of your skull, wondering, what can I do that's going to be fun, interesting, and mildly educational on a Saturday night at 8 o'clock? Do join us in the chat room, say hi, ask questions. We always love to see people there. In addition, you can check us out on our website. That's where you're going to find a list of all our member clubs, because we are a club made up of other clubs. And one of the easiest ways to get into astronomy is to find your local club. So if you're wondering, hey, is there anything closer by? We do have a map inside. We also have brochures for all our member clubs. And not only that, but we have links to all of those clubs that are part of us on our website. Do check them out. In addition, we have a list of all our upcoming talks and past talks with links to those. So do check that out. Another way to keep up with us is to check out our social media pages, our Facebook, Instagram. We have a Discord server. All great places to see what we're doing, keep in touch, or even just share your astrophotography photos or your latest, greatest gear. All right. And one other thing to mention, we are a nonprofit, and we are currently fundraising to build the observatory that will house the 25-inch scope donated from one of our member clubs, Northwest Jersey Amateur Astronomers. It is a 25-inch scope, and we're hoping to break ground this year. As you can see, each of those sheds over there, for everyone who's here, you could see at least. Online people, you can't currently. Each of those sheds with the roll-off roof, that's kind of what we're going to be building to house that telescope. So for everyone who's already helped support that, we thank you. And everyone who is going to, we also thank you. So before we get started in the talk, a few safety points to go over. If you guys need to use the restroom, that is the porta potty in the back. It is to my left, your right. It is big, it is blue. When it gets dark, it is illuminated by red for ease of finding. Speaking of getting dark, it is a state park. It does get quite dark. So as we are wandering around, we ask that we just keep any flashlights we have pointed towards the ground. We understand you might need to see where your feet are going, but trust me, I've had it done. Having the latest, greatest 100,000 lumen monstrosity from Amazon shine directly into your retinas is in fact no fun. So let's try and avoid that. That being said, what's even less fun is getting run over. So as we are driving away, we are using our headlights. Let's avoid that paperwork and those medical bills. There were couple chuckles out there, so at least someone's going, yeah, let's go avoid those. Like I said, I have mentioned the sheds, the ones with the roofs rolled off. Each have a volunteer who is manning a telescope. Feel free to ask any and all questions you might think of and see what they're viewing through the telescope. Also to mention, we have a little museum and gift shop area. Feel free to check it out. There's fun meteorite displays and all sorts of other stuff. But you're not here to listen to me blabber on forever. You're here for our talk given by Walt Windish. Today we're learning about the life cycle of stars. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, just in time to see Halley's Comet. Walt is a member of North Jersey Astronomical Group and Rockland Astronomy Club, and has been volunteering here at Jenny Jump for over 20 years. And with that, here's Walt.
Thank you. And thanks all for coming out, even though the skies aren't that great. Maybe we'll get lucky and we'll see a Jupiter pop out or something like that later on. How many of you are camping overnight? Oh, cool. Perfect weekend for it. Nice. Tonight I'm going to be talking about the life and death of stars, or the life cycle of stars. It's a talk I do every year because I think it's kind of foundational to astronomy. And I try to switch it up a little bit by concentrating on different aspects. I talk about the life and death of a star the size of the sun, go through larger stars, and then tonight I'll be concentrating more on black holes, but we'll be talking about planetary nebula, neutron stars, and then we'll end up with black holes. But a couple of basics that help you if you come up here a couple times or you talk to another astronomer. Okay. I got a space bar. There we go. The first thing I'd like to talk about is magnitude. And astronomers talk about apparent magnitude and absolute magnitude. Apparent magnitude is just as it sounds. It's the way the stars look at us, look to us. When we see a brighter star or a dimmer star, it helps us find our way around the sky. And before we had GPSs, yeah, I'm that old, but before we had GPSs, the way I used to find my way around the sky was I'd look for a bright star, and then I'd star hop to a little dimmer star, and then a dimmer star until I find the object that I was looking for. So magnitude is very important. I'd have a star atlas, and I'd look at the star atlas, and that's how I found my objects. Now you can just dial in the GPX, and the star telescope goes right there. So if you have two cars and one car's headlights is brighter, the two cars have the same brightness, but one car is closer and one car is further, the apparent magnitude of car A is going to be brighter, even though they're the same strength light. But if you have a truck with much brighter lights and they're at the same distance, you're going to see one with brighter light and one with a dimmer light. And that would be an example of apparent magnitude, absolute magnitude, because they're at the exact same distance. But not all stars at the same distance. So what do we do about that? Well, what we do is we normalize the luminosity of a star. We adjust the luminosity for stars to 10 parsecs, which is about 32 light years. So when you see the absolute magnitude of a star, it's the magnitude of a star as if it were 32 light years away from us. And that's all normalized. For apparent magnitude, it's just the magnitude that it looks like. And I'll show you that scale in a little while. Now, when we're talking about planets, what they do for absolute magnitude is they normalize it at 1 astronomical unit. And 1 astronomical unit is the distance between the sun and the earth. So when they talk about the absolute magnitude of a planet, it's as if the planet was sitting where earth is. And that would be how bright it is. So here's a list of stars and their absolute and their apparent magnitudes. And you know, apparent magnitude goes back about 2,000 years with the Greek astronomer Hipparchus. And some say it was Ptolemy that put it together. But they used to say the brightest stars are stars of the first magnitude. It wasn't super scientific, but they just said that's the first magnitude star because it's the brightest, then second magnitude, and so on. And over the years, scientists have adopted that, but it was very inaccurate, or as far as the magnitudes of the stars, and they had to start adjusting different stars. And so you'll see Betelgeuse is 0.8 because it's brighter than a first magnitude star. And you get Sirius is negative 1.5. So the lower the number on the scale, the brighter the star is to your naked eye. And your eye can see to about magnitude 6.5. If you're using a star atlas's listed magnitudes will all be apparent magnitude, what it would look like to your eye, so you can tell what the brightest stars are that you'd see. You see a full moon is negative 12.5 and the sun is negative 26.8. Binocular limit is about 10th magnitude. So you can see dimmer stars with binoculars than you can with your eye. The 1 meter telescope limit is about 19. Limit of the Hubble and Keck is about 30. So that's seeing pretty deep into the sky. And the new James Webb telescope is listed as a magnitude of 34, but it really is dependent on how long an exposure. If they keep spending more and more exposure time, they're going to see further than 34, magnitude 34. So the James Webb telescope is amazing. And I do an update on that every year. This one's, I think it's August 8th. And just what they discovered in the last year, or how they've befuddled scientists in the last year. One last thing we need to talk about is the electromagnetic spectrum. Our eyes only see that little tiny sliver called visible light. But there's a whole spectrum of energy out there. From low energy radio waves, like a ham operator would have, and going up to microwaves, infrared rays, then you have the visible light, ultraviolet, X-rays, and gamma rays. And we have instruments that take images in all of these wavelengths. And when they take a picture in anything but visible light, people have to decide what color to portray it. Like the James Webb only takes pictures in infrared. And so what scientists do is they map the lowest wavelength of infrared into red and the highest into blue. And so it's called a false color image, because if it's not visible light, it's all false color image. So the guy who's processing that image has to decide how to lay out the colors. And sometimes what we do to get an even better image is we stack an infrared on top of a visible light and maybe an X-ray on top of that, and it gives us all kinds of information that's not available from any one source. So the electromagnetic spectrum is a really important thing to know. Now, what is that? Well, yes. It's a plot of, it's just a X and Y plot. And, you know, if there was some relationship in your data, you should see some kind of pattern, right? But this is random. But look at this one. Wow, we see some patterns here. There's two gentlemen, Hertzsprung and Russell, made this diagram. It's now called a Hertzsprung-Russell diagram, or HR diagram. Very useful in astronomy, whether we're talking about a galaxy, a universe, a globular cluster, to take a look at a population of stars. And so what we do is we have luminosity, which is absolute magnitude on the left, plotted against their temperature, which is their stellar classification, how hot it is. The hottest is on the left, and the coolest is M on the right. And each star within an area on this diagram have similar characteristics, just like a periodic table would. The difference is a periodic table stays static, whereas an HR diagram, the stars on this area here, called the main sequence, are stable. They've reached hydrostatic equilibrium. So they're stable for most of their life. But after they burn up their hydrogen, depending on their size, as we're going to see, different things starts happening, and they move off of this main sequence, and they might go to a giant or a supergiant. They might totally burn themselves out after that and end up in the white dwarf area. So the stars move on this chart. Of course, they don't move in the sky as far as changing weird positions. They just change color and they change temperature. And that's what this diagram is trying to show. So from the location of a star on a graph like this, the luminosity, the spectral type, the color, the temperature, the mass, chemical composition, age, and evolutionary history can be known and illustrated on this chart. This looks like a dot matrix printer, though. There's more exciting ways to show the data. Here's the same information in color. And our sun's right here, just sitting in a very boring spot, which is a good thing as for us people on Earth, that it's sitting in a very boring spot. And so it's on the main sequence. That means it's stable for now. Those are stars at rest. As I said, when the stars run out of hydrogen to burn, then they start moving around and they start changing materially. This is a chart that just shows a lifespan of a star. Now, mass mass and luminosity on the HR diagram are compared to the sun. So a mass of 1 is a mass similar to our sun. A star of 1 is our sun. And so you can see down here on the bottom, a star with a mass of 1 is expected to live about 10 billion years on the main sequence. And the spectral type is G2. It's cool compared to others. 0.1 can live for trillions of years. We don't know because the universe isn't that old yet. But like a brown dwarf and red dwarfs, they will last for trillions of years. But as you get bigger, like you get up to 60 solar mass, a 3 million year lifespan is very short astronomically. I mean, they're like the James Dean of stars. They just burn themselves out very quickly. And they go bright, they go big. So here's an HR diagram with the lifespan added. It's just showing longer up to shorter. So it's showing lifespan 10 to the 7th year up here, where you get lifespan 10 to the 11th down here. And it's just showing different stars again. There's our sun. And that's my favorite pretty HR diagram. That's from Astronomy Magazine. And again, the sun is there. It's a G-class star. And it's a real, right in here, that's our sun. It has an effective surface temperature of about 10,000 degrees Fahrenheit. Since luminosity and mass of all other stars are measured relative to the sun, as I said, the sun has 1 solar luminosity and 1 solar mass. And that you can see there as well. Stars become main sequence when the process of thermonuclear fusion, converting hydrogen to helium, stabilizes. And about 90% of the stars in any given time will be found on the main sequence. But I like this chart because it illustrates why some stars are brighter. So you can see amongst stars of the same size, the hotter ones are brighter on the left, and the warmer ones are cooler. Of the stars of the same temperature, the smaller ones are less bright, duh, and the biggest ones are the brightest. So it shows there's 2 reasons for a star being bright. It's either going to be really large within its class, or it's going to be really hot within its class. These stars are much hotter, much brighter than these stars, even before they get to be really large stars. So let's take a look at the life cycle of a star, an average star, 1 to 8 solar masses. That would be the top path up here. This path produces no supernova, but a planetary nebula and a white dwarf, which is where our sun's headed towards. Larger stars, more massive stars, above 8, will go down the massive star, and we're going to talk about each of these in a little more detail. They produce supernovas. Between about 8 and 60 solar masses will produce a neutron star. Over 60 solar masses will produce a black hole. So right now we're interested in that top path, the path of an average star, 1 to 8 solar masses. So the nuclear fusion creates an outward pressure. Once the gas collapses, it gets hot, it heats up, the gravity collapses it, it gets even hotter. And then finally you compress the atom so tight that you start getting nuclear fusion, and then you get the radiation. So that's the outward pressure on the star. Gravity is the inward pressure. Gravity is looking to suck the star in. The fusion, which is like explosion after explosion, is pushing it out. So when it finally, after about 100 million years, it finally stabilizes. The pressure on the inside and the pressure pushing it outside stabilizes, and it reaches hydrostatic equilibrium. And then it's considered a main sequence star. And depending on the size of that star, will determine how long it's going to live and how long it's going to stay on that main sequence. As the star nears the end of its hydrogen supply, the core shrinks and gets hotter and burns the remaining hydrogen at a faster rate. The hotter core radiates more energy and pushes the outside layers out, which cool and become redder. So the outside layer becomes cool, redder, and it starts to expand and become a red giant. And then it leaves the main sequence, as we shall see. This shows how our sun is going to leave the main sequence. So our sun sits here for about 10 billion years. And the last billion or so, it goes up and down. And again, remember, it's not really going up and down physically, but it's getting, if it goes up here, it's getting what? It's getting brighter. And if it goes this way, it's getting hotter. So it's showing our sun getting brighter and then hotter and then cooling down. That's how you read that diagram. That's what happens when a star the size of our sun. So what happens is the outside shell gets cooler and starts expanding and becomes a red giant. So we see that subgiant becomes a red giant. And then at one point we have something called a helium flash where it starts burning helium. And we can see the helium flash on here as well. Helium burning star. And then it gets to be an even bigger red giant. And it burns through, if it's about 2 solar masses, it'll burn all the way up to carbon and a bit of oxygen. A star with 1 solar mass won't get that far. It'll go hydrogen, helium. But the star itself becomes smaller, hotter, and bluer, as shown by this second leg. At some point, gravity loses, and the outer shell blows off into what they call a planetary nebula. And what's left is about half the mass of our sun in a size of our Earth, which is pretty amazing. It's very, very dense. So you have the protostar, the main sequence, the red giant, the helium flash, then it goes to the giant branch, planetary nebula. Planetary nebula has nothing to do with planets. When they were hunting comets in the 1700s, they were seeing these faint fuzzy things that looked like planets, but they weren't planets, and so they called them planetary nebula. And what they were the shell of these dead stars. A planetary nebula will only last for about 20, 30,000 years or so, and then it just dissipates. It's a gas cloud that's being heated by the white dwarf. The white dwarf can last trillions of years, but the gas cloud around it gets blown off. So our sun is currently around 4.5 billion years into its 11 to 11.5 billion year life cycle. 10 billion years it's going to leave the main sequence. This just shows a cross section of a star approximately 2 solar masses, where it goes a little further than helium. We saw how helium, as a product of fusion of hydrogen, became the next fuel for the star. Well, if it's 2 masses or more, it won't stop there. It'll keep burning until it gets down to the carbon oxygen. And the last bursts of energies push the outer core away, and the ultraviolet radiation from the star ionizes that gas in the shell, setting it aglow, and it forms often a very beautiful planetary nebula. I'll show you some pictures of it. And what's left behind again is a very small core, the size of the Earth, known as a white dwarf. So what do these planetary nebulas look like? Well, that's the Ring Nebula. If you come here on a cloudless day, you'll see straight up is the constellation Vega, and we often get this object in our telescopes. What it'll look like is a very tiny smoke ring with no color. Your eye is about the same as a 1/30th second exposure on a camera. Not enough to gather enough light to see any kind of color. So what we do is we do astrophotography. And matter of fact, I'm doing a talk next month on astrophotography from New Zealand. I've got some pretty cool stuff. But if you have longer exposures and stack them now with modern electronics, we can stack 20, 30, 40 exposures on top of each other. We get some amazing pictures. And of course, this is like a Hubble spot. But there are some amazing pictures that are being done by amateurs as well. The inside star, the white dwarf, is 15th magnitude. Right there, that's the star that blew off the shell. Heat produced or heat radiated is no longer produced by nuclear fusion. Just a super high density of gravity, metric ton per cubic centimeter. Now, I talked about the electromagnetic spectrum. If you add some infrared photography to this, we get a little different picture. That nebula in the center is the same ring nebula I just showed you. But now with the infrared, we could see the result of when that star was a red supergiant before it collapsed back in. And you can almost see the shock waves coming out of that in the infrared. And so that red portion was formed about 100 million years before the white dwarf tore away. I'm sorry, 10,000 to 100,000 years early. We're not quite sure. The Large Binocular Telescope and the Subaru Telescope on the ground in Hawaii provided us with the infrared imaging there. Here's another one, the Dumbbell Nebula in Vulpecula. This is another summer object in the northern hemisphere. It's about 1,200 light years away, and it was first described by Charles Messier in 1764. Charles Messier was a comet hunter, and he's the guy that saw these nebulosities, and he didn't want to get sidetracked from his comet hunting, so he cataloged all the stuff that looked like it might be a comet but wasn't a comet. And that's the Messier catalog that we still use today. This is another amazing one. This is called the Cat's Eye Nebula. It's a real head scratcher for scientists because there's a pattern of 11 or more concentric circles, and there's all kinds of theories about how that was formed. Probably the leading theory is that the star was pulsing at 1,500-year intervals, which created these rings. These rings are really bubbles around it. We're like, if you take an onion and you cut the onion, then you can see the rings. That's what we're looking at here. These are actually 11 bubbles that encircle that white dwarf. And just an amazing image. This one's called Hubble's spirograph for obvious reasons. IC418. It glows like a multifaceted jewel. This is a southern hemisphere object. It's about 2,000 light years from Earth in the direction of the constellation Lepus. So all of these planetary nebula started out similar to our sun. They became red giants, then the outer atmosphere drifted off, and what's left is called the white dwarf. And it's so dense that approximately half the mass of the sun is packed into the sides of our planet. So think of the half of the sun being packed into this. It's just amazing. And this is the least dense object that we're going to talk about tonight as far as a remnant. But first, let's just get an idea of the size of some of these objects. This isn't a star. I just wanted to start here because it's kind of an interesting slide. About 28 years ago, comet Schumacher-Levy broke into 21 fragments, and they hit Jupiter. And those plumes are what comet Schumacher-Levy left behind. So we're looking at Jupiter. And the reason why I use this slide is because the size of those plumes are about the size of the Earth. The Earth is about 7,900 miles in diameter. The moon's 2,000 or so, 2,159. So a white dwarf is similar to the size of the Earth. So those plumes show you what Earth and also what a white dwarf looks like against Jupiter. Now Jupiter is 86,881 miles in diameter. The sun is 864, so it's 10 times the diameter. And it's 10 times the diameter, but about 1,000 Jupiters can fit into the sun. So that gives you an idea of the scale. And the sun, again, you saw, is one of the small guys, one of the boring ones. So there's our sun. Our sun makes its appearance. And it's not looking all that huge against these stars. Arcturus is a star that we can see very easily. If you look at the Big Dipper, you know how the handle is curved. Call it the arc of the Big Dipper's handle. Follow the arc to Arcturus. The next bright star you'll see is Arcturus, the brightest star in Bootes, and it's a red giant. And it's looking pretty big. The diameter of Arcturus is 22 million miles. So it would reach about 2/3 of the way to Mercury if it was where our sun was sitting. Now Arcturus isn't looking all that big. There he is. The red giant Betelgeuse, which is one of my favorites. That's the left shoulder of Orion the Hunter. We see that in the wintertime. It's got a diameter of about 765 million miles. It's 700 light years away from us. And now if this Betelgeuse were where the Earth was, we would be way inside it, and Mars too. And that's actually what's going to happen to us when our sun turns into a red giant. We'll be inside of the sun, the outside of it, because it'll be about the size of a Betelgeuse. You can fit 1.3 million Earths inside our sun, and you can fit 700 million suns inside a Betelgeuse. So it's a pretty big star. Betelgeuse is called Alpha Orionis. When you look at star map, they use Greek letters for the stars, and the Alpha star is the brightest, and then Beta, and so on. So if you hear Alpha Orionis or Alpha Scorpii, you will know that's the brightest. Arcturus is Alpha Bootes. It's the brightest star in Bootes. Betelgeuse is also the 9th brightest star in the sky, and it's part of the winter triangle. Now in the summertime, you should be trying to find the summer triangle, which is Vega, Altair, and Deneb in the Northern Cross. Now Antares, again, which is bigger than Betelgeuse, is about 604 light years from Earth and 700 times the sun's diameter. Then we get to some of the biggest ones, and the biggest one's always changing. I usually check before I do my talk to see if they found yet another bigger one, but I didn't bother this time. But VV Cephei in the constellation Cepheus is one of the biggest. There's some that are bigger, but it's one of the biggest. Its size is uncertain, but it's about 1,000 to 1,900 solar radii. We're constantly finding new stars. One of the newest big ones is UY Scuti. And while that's the largest star, there's a star R13.6. It's currently the heaviest star in the universe. It's in the Large Magellanic Cloud, and that's about 165,000 light years from us. And it's a rare class of hypermassive stars. It's about 170 to 230 times the mass of our star. So as we saw, there are plenty of stars that are bigger than our sun. And so we'll just take a look at the bottom line and see where they go. These stars that are over 8 times the size of our sun won't experience that helium flash I mentioned. They will keep going. They'll go through carbon, oxygen. They won't float quietly into space as one of our stars would. Just like the low mass stars, the monster stars started with a collapsing gas cloud, and once they get past the oxygen, they'll keep going Oop. These will keep going until iron is produced at the core. Iron, no star gets past iron. Iron is the tragedy for any star because iron is the first element that does not give off energy but requires energy in fusion. And so when it hits iron, what happens is you get a core collapse supernova. The star just collapses in itself and then explodes in a bright supernova. This just shows the two paths of a 1 solar mass star on the bottom right and a 15 solar mass star that just is going through the elements. And that when the supernova explodes, that's how elements are put into this universe, right? It's got all those heavier elements, and they, as that star explodes, they're all over the place. For a brief period of time, the light that's generated by a supernova, and that's a picture of a supernova on the bottom right, you just can't capture how bright it is on a camera. You just overload the wells, and it just doesn't do it justice. But they explode with a luminosity of about 1 billion suns. They outshine the galaxy that they're in. They're so bright that they're visible at immense distances. If a nearby star was to undergo a supernova explosion, it would be so bright it would be visible during the daytime. And that has not happened in modern days. However, Tycho Brahe and Johann Kepler both observed naked eye supernova during their lifetimes. This one occurred in the Large Magellanic Cloud, which is a companion galaxy. It's a dwarf galaxy. It's naked eye in New Zealand. When I went down there, I could see it naked eye, the Large Magellanic Cloud. So in 1987, this supernova went off about 50,000 parsecs away, 163 light years. Ground-based telescopes picked up this image about 2 weeks after the explosion. And note how bright that exploding star is. Again, it doesn't do it justice. There's a Hubble telescope picture of it. Again, looking at the remnant of the 1987A, and you can see the shock waves still years afterwards. Now, I spent quite a bit of time on neutron stars and supernovas, so I'm not going to spend a whole lot of time there because I want to get the black holes. But here's an artist's rendition of what a supernova shock wave looks like during the explosions. And what's left when a supernova starts with a star under 60 solar masses is a neutron star. This is an odd neutron star. Yeah, it's also a lone neutron star. But a neutron star can have a greater mass than our sun and be only 12 miles or so across. So the sun weighs 333,000 times more than Earth. So imagine a mass of 166,000 Earths packed into the area the size of Manhattan. And that would be your neutron star. And then set it spinning around. Some of them spin at 30 times a second. The highest one was clocked at over 700 RPS, revolutions per second. So we're talking about a tiny star that's 1 trillion times more dense than our sun, all packed into a little 12-mile or so area. And if that's not enough, as I said, they spin up to 716 revolutions per second. Theoretically, they could go at birth, they could go as fast as 1,000 to 1,500 revolutions per second. This is one of my favorite nebula that houses a neutron star. It's the Crab Nebula, which is a winter object in the northern hemisphere. It's 6 light years across uh, as a remnant. What I really like about it is in 1054, Japanese and Chinese astronomers recorded seeing a daytime object, which was this star going supernova. So about 1,000 years ago, um, this thing went supernova, and people who were here on Earth were able to see it and saw it as a daytime star. Just amazing. And it spins around also like a lighthouse, ejects twin beams of radiation. This one rotates about 30 times per second. So it means a point on the star's equator is traveling at 3.4 million miles per hour to do that. And neutron stars are the only type of star that can rotate this rapidly without breaking up, and that's because they're so dense. Oh. This is an image of the Cram Nebula from 3 different spectrums: visible light from the Hubble, purple X-ray from Chandra, and also the X-ray observatory, and infrared light from the Spitzer Space Telescope. So those were all combined to give us this. We can see the relativistic jets coming out of one side as it gobbles up material. This is an artist's rendition of another common neutron star configuration, one with a companion star that it's cannibalizing. And this is pretty common for a companion star to be near a neutron star, or especially a black hole, and then have it being eaten up. And as I said, I'm just going past the neutron stars. I spent a lot of time on it before. I want to get to the black hole, which we are finally at. If you're over 60 solar masses or so, the remnant left behind will be a black hole. So this is an artist's rendition of a black hole. It's about 80 solar masses, and after 80 solar masses, we think we get a black hole. Although we can't see the black hole, we can see their effect. Black holes are so massive that they bend the fabric of time and space. Albert Einstein's general relativity equations predicted it, and we have certainly confirmed it beyond any reasonable doubt anyway. If you compress the sun down to a black hole, it would be about 6 kilometers in diameter. Sun right now is 1.4 million kilometers. But we don't have to rely on artist renditions anymore. Not since 2019. The image on the left is a supermassive, we now have some images of the black hole. We actually, what we're seeing is the accretion disk. Since a black hole doesn't even let light escape, you can't photograph the black hole, but you can photograph the silhouette of the black hole, because it's eating up so much material that material is spinning around the black hole, getting hotter and hotter, and we can photograph that, or image that heat. We use a special telescope called the Event Horizon Telescope. It's named after the event horizon of a black hole. The event horizon is the point at which light cannot escape. And the Event Horizon Telescope is actually a global network of synchronized radio telescopes that function as one Earth-size scope. And using that, and along with very long baseline interferometry, it achieves a high enough resolution to capture the area around a black hole. And that's what we're looking at. The image on the left was the first black hole image to come out. It was of the heart of M87, which is an elliptical galaxy in the Virgo cluster of galaxies, about 55 million light years away. Over the course of 4 nights in 2017, the data was collected, and then a team of astronomers wrote software to actually process this to give us the image that we're now looking at. And that was released in 2019. This is an image of M87, the elliptical galaxy about 55 million light years away from Earth. Unlike the Milky Way's stunning spiral arms, the M87 is a blobby giant elliptical galaxy. Not too exciting. I wouldn't spend time doing astrophotography of that galaxy, but it's pretty cool when you know what's behind it. Now, the image of the right is our very own black hole at the center of the Milky Way. It's known as Sagittarius A star. And we can see Sagittarius on most summer nights looking southwest. So when we look at Sagittarius, what we're doing is we're looking towards the center of our galaxy. And there's all kinds of cool objects to look at and photograph because it's so dense. We're looking through a really dense part. And so that is an image that was released in 2022, only about 4 years ago, of our own black hole. Now they look similar when you look at these two, but they're very different in size. The M87 black hole on the left, the first one we imaged, its mass is 6.5 billion times of our sun. So there's a mass of 6.5 billion suns in that black hole. The event horizon, also known as the Schwarzschild radius, is 240 times the distance from the sun to the earth. Now that distance, 93 million miles, you can call it 100 million miles. So 240 times that, anything around that black hole, light is not going to escape. That's a huge radius. The bright area around the light is emitted by gas and dust that are spiraling into the black hole, that have been trapped by its gravity, and as it eats them up, they just accelerate and they get really, really hot. So the image at the right, the one at the center of our galaxy, is 4.31 million solar masses. That's compared to the 6.5 billion. So we're talking about a magnitude of about 1,500 there in mass between ours and the one that we imaged. So the glowing disk of our black hole would easily fit within the orbit of Mercury. So it's not too big. We got to remember how dense the black holes are. They're so compact. One other recent development in the areas of black hole that I thought I'd share with you. Let's see, is the collision of two black holes. It was detected for the first time ever in September of 2015. Laser Interferometer Gravitational Wave Observatory, or LIGO, is what detected it. And this, what we're seeing here, is a still from a computer simulation from the LIGO Caltech website. So they used data, fed it into a computer, and gave us this owl-like representation of what happened. The two merging black holes were each roughly about 30 times the mass of our sun. One was 29, one was 36. So they're pretty small compared to what we were just looking at. The event took place 1.3 billion years ago. So how do we know about it? Well, our telescopes are like time machines, right? Does anyone know how that would be? How a telescope could be a time machine? Yeah. Yeah, that's great. Or a billion, right? So this event took place 1.3 billion years ago. It took the light 1.3 billion years to get here. So we're just seeing it now. Just like when you see the light from the sun, you're not seeing the light that's happening right now. You're seeing an 8-minute delay. It takes 8 minutes for the light from the sun to get here. When you say there's an object 1,000 light years away, when you're looking at it through the telescope, you're looking at that object, how it appeared 1,000 light years ago. That's why a telescope like James Webb is so important, because when we look back at an object that's 13 billion years, light years away, we're looking at how the object looked 13 billion years ago, only 800 million years from the beginning of the Big Bang. And so we're looking at early galaxy structures, early star structures, the compositions there. And if you come to my James Webb talk, I'm giving myself all these advertising, August 8th, you'll see there are a lot of discoveries that James Webb has turned up that are just befuddling scientists, because they're looking at their cosmological model and they're saying, you know what? This doesn't fit. These galaxies are much better formed than we ever predicted, and they're occurring much earlier. And there's more diverse elements in stars earlier than we thought. And so, as we look further back in time, we're getting more and more information about how galaxies form, how stars form, and how the cosmos just came into being. So here we detected two black holes colliding 1.3 billion years ago. And according to the LIGO website, the black holes warp space and time, and this causes light from the stars to curve around the black holes in a process called gravitational lensing. So they bend space-time so much that we can see objects behind the black hole because they're curving around to the side of the black hole. And I've got some other pictures I'll show you. So the ring around these black holes, they're known as Einstein rings, and they arise from the light of all the stars in a small region behind these black holes that bend gravitationally and their images get smeared into a ring. And let me give you a quote. This is one last thing I'll say is that the collision that was detected by LIGO and its sister Virgo lasted about 0.2 of a second. So the collision, when they finally collided, took about 0.2 of a second to happen with these huge objects. And the peak power output of the collision exceeded that of all the stars in the observable universe by a factor of 50. It's just mind-numbing. I can't even picture that. So you have a supernova, that energy light output can exceed its galaxy, but this one we're talking about the observable universe from a collision of black holes. And a quote from a book that I'm reading right now called Black Holes, The Key to Understanding the Universe. Really interesting fact. It said, by the time those ripples, the ripples of that collision of the black holes, by the time those ripples reached us 1.3 billion years later, they shifted the 4-kilometer long laser ruler arms by 1/1000th of the diameter of a proton in a fleeting, wiggling pattern that exactly matched the predictions of general relativity. That's just, I don't know what is more mind-boggling. These two black holes colliding and giving off more energy than the observable universe for a split second, or the fact that we have these laser rulers that are 4 kilometers long, and we can measure an irregularity in that ruler that is 1/1000th the diameter of a proton. I can't believe how amazing the measurements are that we have now with our current technology. Yeah, and the LIGO is a laser measuring device, and they measured a disturbance in that laser that was 1/1000th of a proton in width, and the wiggle that they observed matched the relativity, the prediction of general relativity. So since 2015, these detectors have detected a bunch of black holes. I don't know what the latest number is, but they have gone on to detect more black hole mergers. And the discoveries have proved to be, these discoveries that I've just discussed prove that these objects actually exist. Actually, they give us evidence that's pretty hard to refute, because when people worked general relativity equations and came up with these black holes, it was viewed as just a weird quirk of general relativity, that it was an outcoming of the equations, but everyone knows that these probably don't exist in nature. Well, they do, and we have now have close to irrefutable evidence. I'll spend just a couple minutes talking about gravitational lensing. Gravitational lensing is when a very massive object disrupts space-time so much that we can see behind it because the light is curving around. And it very much distorts whatever's behind it. Here we see a cluster of galaxies about 5 billion light years away from Earth in the middle. And that curved arc is a galaxy that's actually another 5 billion years behind that massive galaxy. So about 10 billion light years from us. And it's being distorted, but it's also, we can see behind that cluster of galaxies and see the galaxy behind it. So another cool effect that Einstein predicted, and it took us years to actually witness, is an Einstein cross. This particular Einstein cross was formed by a supernova. Again, we have a very massive cluster of galaxies about 5 billion light years from us, and a supernova went off, and we saw, this is a magnified area, we saw 4 instances of the same supernova being bent by the fabric of time, and we were able to photograph that. One other Einstein cross was from a quasar. Again, there's a very massive distant galaxies, and the galaxy causing the lensing is about 400 million light years away, while the quasar that is being lensed, and we see four images of it, is about 8 billion light years away, almost 2/3 the age of the universe. And so I'll end with one last gravitational lensing known as gravity's grin. There's 2 distant galaxies there that are imaged in the X-ray and in optical data from Chandra and the Hubble telescopes. It's nicknamed the Cheshire Cat Galaxy Group for obvious reasons. The group's 2 large elliptical galaxies are suggestively framed by the arcs of galaxies that are being gravitationally lensed because of their mass. And the 2 eyes represent the brightest members of their own galaxy groups, which are merging. Their relative collisional speed is about 1,350 kilometers per second, and it heats gas to millions of degrees, producing that purple X-ray glow that's shown in purple hues. The Cheshire Cat Group is in the constellation Ursa Major, which also houses the Big Dipper, so we see that all times of year, and it's about 4.6 billion light years away. So there we have it. There's the life and death of stars from our sun and a planetary nebula right down to the massive stars that produce black holes. Hope you found something interesting in there. Thank you.
All right. Thank you, Walt, for another great talk. So we are going to have a question and answer session. But before we get into that, I saw a couple people sneak in during the presentation, and the safety briefing is in fact inescapable. If you guys need to use the restroom, that is the porta potty in the back. It is to my left, your right. It is big, it is blue. It is now illuminated by red for ease of seeing, now that I remembered to turn that light on. We also have a little museum and gift shop area. Feel free to check that out. Our meteorite display and all sorts of fun things like that. We do have a number of telescopes open. Each shed with its roll-off roof houses its own telescope and hopefully a volunteer. Feel free to ask any and all questions you could think of. See how many times you can stump them. He's laughing because in about a minute, I'm going to suggest you try and stump him with questions too. But spreading out the fun torture. Since it is getting dark, If we have any lights that we're using to wander around because we like to not trip over our own feet, um, do try and keep those pointed towards the ground. We don't want to accidentally blind people. That being said, we are using our headlights when we leave. Being run over is no fun, and ain't no one need to have a trip to the emergency room at 9 o'clock on a Saturday night. Usually that's a busy time. Let's avoid that. So, how question and answer session is going to work. For the people here, you're going to raise your hand and wave it about and keep your hand up and moving slightly so I can see it. I've been monitoring online chat, so I have no night vision. So as soon as you put your hand down, you blend in with the shadowy figures in the dark. I need distance glasses, and unfortunately, if I have my distance glasses, I can't see chat. Online people, you have it easy. You just type in your question, and it shows up on my wrist-mounted chat. With that, we're gonna get started with our first online question, which is, how old is GPS?
GPS? Oh my gosh.
I did take the
GPS and telescopes. I GPS is, I don't know how old GPS is. GPS and telescopes showed up in the 1990s.
So I did Google this for the sake of knowledge, and because at first I thought I was older than GPS. I am in fact not older than GPS as the whole thing, because the first experimental GPS satellite was launched into orbit in 1978. However, in 1993 is when the system reached initial operational capability. And by 1995, the U.S. military declared the GPS fully functional. So commercially available citizen-held GPS was in the early 1990s. So, fun facts. All right. Any questions out here? Keep in mind, if you kind of don't move around, I can't. Is that a question in back, or is someone just packing up?
Swatting a mosquito.
Yeah. By the way, going forward, we are coming into the hot part. You might want to bring bug spray. The mosquitoes get fierce and can carry away small children.
Hey, great presentation, by the way.
Oh, thank you.
Yeah. Just maybe a quick note to add probably the next time around. You mentioned how when the star reaches, if it's about 2 times the size of the sun, it goes into white dwarf and has ability to go into the neutron star. Just a quick note there. Dr. Chandrasekhar, who is an Indian scientist, he predicted, or he actually gave it the formula that 1.44 the times of sun, essentially if that's the size of the sun or bigger, that's when a star actually becomes a neutron star from a white dwarf star. So
that's called Chandrasekhar
Chandrasekhar limit.
Limit, right? Yeah. Yeah. Thank you. Thanks for adding that. I'm sure I butchered his name, but
All right. I see another question back here.
If the sun eventually like disappears because it turned into a white dwarf and then like explodes or something, what will happen to the Earth?
The sun isn't going to disappear. What's going to happen is it's going to turn into a red giant, and way before that, it will be too hot here for life. So, before right around the 10 billion limit or so, it's just going to be too hot to live here.
And after that, the sun becomes a very large amoeba and goes numb.
Yeah, we'll be inside it.
But I won't have to worry about that. So yay!
I don't know what's going to happen first, the red giant or if the Andromeda galaxy is going to collide into us. It'll be interesting. They're both around the same timetable, around 5 billion years.
Someone in chat wanted to be a little cheeky. Is James Dean the government name for Jimmy Dean, the breakfast sausage?
Oh my goodness.
Or is Jimmy the cousin twice removed?
Okay.
All right, I saw another question out here.
Quick question on the HR curve that you showed.
Yeah.
Where would you place a black hole? Would it be top left, or
Oh, interesting. It would be the bottom. I think it would be the bottom right.
oh, close to
It's a tough one because nothing escapes the black hole, and so on the top left is very bright, and the black hole is the exact opposite of that, and it's smaller than the red and the brown dwarfs, although the density is amazing. Yeah.
I think perhaps to visualize it, you would need to add another access, like going forward and back, to also then take into account density, if that makes sense. Like instead of a 2D scatter plot, you have a three-dimensional one.
Yeah, it's just such a totally weird object. Instead of cooling down like a white dwarf, you've got this Hawking's evaporation. That's a theoretical evaporation of as a black hole. If there were enough billions or trillions or quadrillion years, that it would slowly evaporate away. But that's going into way over my pay grade. That's some heavy duty mathematics.
This is more of like a personal question, but I'm not really too crazy about learning too much about space and stars or anything like that. My boyfriend kind of dragged me here, but I found your slideshow pretty interesting.
Oh,
And I just
thanks.
wanted to ask, what kind of films do you prefer? Like, is there a favorite film about space that I don't know, either you grew up with that you like, and like kind of like what it inspired you maybe with your passion, but like also what do you recommend to
Well,
watch?
that's a great question. I'm not even sure. I mean, I grew up. I read science fiction books, but a lot of my love for science came from reading books. There was Carl Sagan's Cosmos. Nowadays, what I'll do is I'll Google stuff on YouTube. And I'll Google stuff like black hole or cosmology, and look at what pops up on the menu, and take a look at that stuff. But not really a whole lot of popular science movies. Just a lot of books that I'm really enjoying. There's a popular science book I'm reading right now that's called Black Holes: The Key to Understanding the Universe, and it's written in very understandable prose, and it's only about 3 years old, so the science is pretty new, and I'm really enjoying that. I haven't even finished that yet, but thanks for the question.
All right, online people, I would just want to give you a heads up. If you have any questions, do get those in. I like to tell them because much like it takes a light time to get from a distant star to us, by the time they hear our message, we are a couple minutes into the future. Our next online question actually came from a couple weeks ago, and I
You
held
saved
on.
it for me.
I held on to it because I believe you have some insight. Uh, any familiarity with the Dwarf Mini Smart Telescope and how I think you have a dwarf.
I have a C Star S30, and the Dwarf Mini is a very nice portable telescope, and for the price, you really get a lot of bang for your buck. It's not going to take the pictures of a $1,000 or $2,000, but you can throw this in your carry-on luggage with a little tripod, and you can take some really nice pictures. A lot of it is the post processing, and again, it doesn't take artificial intelligence and put stuff that's not in your data. It takes your data and it stretches the data as far as it can, as far as bringing colors out of it. The software is very nice. I would look at that, and I would look at the C Star, but the Dwarf Mini is just an amazing price. As a first telescope, I don't think you'd be disappointed. But I think after a year you're going to be looking for something else. But it's not a big risk as far as the money is concerned.
That's kind of like, uh, sure. Let's.
Thank you, thank you. Sorry to interrupt. What made you choose the C Star 30 over the 50? Do you have a Pro or a
I
regular one?
chose, the Pro wasn't out last year. My son told me he was taking me to New Zealand, and that was available. The dwarf wasn't even available. So I had limited choices. In September, I think it's September, I'm going to do a talk on smart telescopes because I've used a Celestron Origin, which is on the total other end of it, and a C-Star, and now this year I went to New Zealand with 30 pounds of astronomical gear, so I can do photo comparisons with each of those, unprocessed and processed, and that's kind of what I'm going to do. But the C-Star S30 Pro is a very attractive package, and the 50 Pro might even be the way to go. But again, my S30 I threw in a carry-on luggage, and I took it to New Zealand, and there was no. This last year I took 30 pounds, and the experience was quite different as far as my back and the bother and the airlines and all that stuff.
I'm assuming you had to put that into checked luggage and declare that this is a telescope, not something weird and.
I hand carried my telescope, but I checked the mount because it was the mount and the tripod. I checked the telescope and the camera I carried, and I was very nervous about the entire situation.
All right. Also, on a note, small telescopes, yeah, you might want a new one in a year, but when you're looking to get into it, the small price point of entry, it's probably a factor. Which is kind of why, like, the telescopes we offer in our gift shop, they're small. You're going to get decent views of planets, some of the brighter objects in the sky, the moon. If you get a proper filter to put on the telescope, even the sun, solar viewing, but they're not going to get you the deep objects, but it'll get you starting to learn how to use and operate a telescope. And sometimes it's a lot better to spend a little bit of money, learn a whole bunch of stuff, and then decide, yes, it is time to graduate to a larger telescope. So there's nothing wrong with going with the smaller one.
No, and then you decide whether you want wider field views or if you want to concentrate on smaller objects, and that will inform your choice of your next telescope depending on where your interest lies.
Or if you're like me and want zero setup, you go for a Dobsonian and go, my base is here, the optical tube's here, and now I can view. I don't want to spend half an hour setting up. All right, any more questions out here? All right, so I'm going to cover the last question here online that I see, which is, do we know when the next daytime visible supernova will be?
No. And don't believe what you read on the internet. No, those we don't know. You know, Betelgeuse is an interesting star. If it went, it would be a daytime star. But with supernovas, you can see them getting close. But, if you're within 1 million years, that's pretty close astronomically. But it doesn't work for me as far as my vacation planning.
And we still have no idea whether this next round for T Corona Borealis being visible at night will be a thing. So, unfortunately, science is still progressing on learning to predict things like that. All right. And someone said hi from their star party in Michigan.
Wow. Hello.
So, hi.
I'm jealous.
Apparently, they had 3 clear nights in a row.
Ooh.
And it looks like we're actually clearing up.
Yeah, it is clearing up.
Without my glasses, I can start to see stars. So, improvements. All right. So with that, I want to thank everyone who's joined us here and online. Like I said, check us out on our website, uacnj.org. We have our social medias if you want to check those out. Facebook, Instagram, our Discord server, all great places to ask questions and see what we're up to. And with that, until next time, clear skies and good seeing.
Thank you.